On April 25, 1986, engineers at the Chernobyl nuclear power plant in Soviet Ukraine were preparing to conduct a safety test. The test was designed to answer a simple question. If the plant lost external power, could the spinning turbines generate enough electricity to keep the reactor cooling pumps running for the 60 to 75 seconds it would take for the emergency diesel generators to start? It was a routine procedure. It had been attempted 3 times before. The engineers expected it to be completed by morning and forgotten within days. Instead, what happened that night became the worst nuclear accident in human history. Reactor number 4 exploded with a force that blew the 1,000-ton reactor lid off the building. The graphite moderator caught fire. Radioactive material was ejected into the atmosphere and carried by the wind across Europe and around the world. 35,000 people were permanently evacuated. The 30-kilometer exclusion zone around the plant remains uninhabitable today, nearly 4 decades later. The total cost of the disaster, in cleanup, evacuation, health consequences, and economic damage, has been estimated at hundreds of billions of dollars. But what makes Chernobyl truly extraordinary is not just the scale of the catastrophe. It is that the disaster was caused by a combination of a fatal design flaw that the Soviet authorities had hidden from the plant's own operators and a series of human decisions made under pressure that removed every safety barrier one by one until nothing stood between the operators and catastrophe. This is the complete engineering explanation of the Chernobyl disaster. We are Mech Cosmos, engineering, explained. Let us begin. To understand what happened at Chernobyl, you first need to understand the reactor that was used. The Chernobyl plant used RBMK reactors, a Soviet-designed graphite-moderated boiling water reactor. The RBMK was a large and powerful reactor design that had several practical advantages from the Soviet perspective. It could be refueled while running without shutting down. It used ordinary, unenriched uranium fuel, which was cheaper and easier to produce than the enriched fuel required by Western reactor designs, and it could be built without the large pressure vessel required by Western pressurized water reactors, making it cheaper and faster to construct. But the RBMK had a fundamental design characteristic that made it potentially dangerous under certain operating conditions. This characteristic was called a positive void coefficient, and understanding it is essential to understanding why Chernobyl exploded. In most Western nuclear reactors, the cooling water serves a dual purpose. It removes heat from the reactor core, and it also acts as a moderator, a material that slows down the neutrons produced by fission to the speeds at which they are most effective at causing further fissions. This dual role creates an inherently safe feedback mechanism. If the reactor overheats, the water begins to boil. Bubbles of steam, voids, form in the cooling water. These steam voids are much less effective at moderating neutrons than liquid water. With less moderation, fewer fissions occur. The power output decreases. The reactor cools down. The steam voids collapse. Moderation returns to normal, and the reactor stabilizes. This is called a negative void coefficient. The formation of voids reduces reactor power, creating a self-correcting safety mechanism. The RBMK reactor used graphite, a solid carbon material, as its primary moderator rather than water. The water in the RBMK served primarily as a coolant rather than a moderator. This seemingly technical distinction had catastrophic consequences. In the RBMK, when the cooling water began to boil and steam voids formed, the loss of the water's modest moderating contribution was more than compensated for by other factors in the reactor's neutron physics. The net result was that when steam voids formed in the RBMK reactor, power actually increased rather than decreased. This positive void coefficient meant that in certain operating conditions, the RBMK was self-amplifying rather than self-correcting. A power increase caused more boiling, which caused more voids, which caused more power increase in a runaway feedback loop. The positive void coefficient was most pronounced at low power levels, below about 20% of the reactor's full rated power. Soviet reactor physicists understood this characteristic. It had been identified and documented. But the full extent of the danger was classified, kept secret by Soviet authorities who did not want to acknowledge a fundamental flaw in their reactor design. The operators at Chernobyl had not been fully informed of the danger of operating their reactor at low power levels. The night of April 25 and 26, 1986, brought together this hidden design flaw with a series of human decisions that systematically dismantled every safety protection the reactor had. The safety test had originally been scheduled for the day shift on April 25th, but at 14 hours, the Kiev Regional Electricity Authority requested that the reactor remain at full power because electricity demand in the region was higher than expected. The test was delayed for 9 hours. During this delay, the day shift crew went home and were replaced by the evening shift, who were also then replaced by the night shift crew. By the time the test resumed at 01 on April 26th, the crew on duty had not been properly briefed on the test procedures. They were tired, and they were under pressure to complete the test before the reactor was scheduled for its annual maintenance shutdown. At 0028, the reactor power was being reduced in preparation for the test. An operator error caused the power to drop far lower than intended, to nearly zero. This was extremely dangerous. At very low power levels, the RBMK was susceptible to a phenomenon called Xenon Poisoning. Xenon-135 is a radioactive isotope produced as a byproduct of uranium fission. It is a powerful neutron absorber. It captures neutrons and prevents them from causing further fissions. During normal operation at high power, xenon is continuously burned off by the intense neutron flux. But when power drops suddenly, xenon accumulates faster than it is destroyed, and its concentration in the reactor core rises rapidly, suppressing the chain reaction and making it very difficult to raise power again. The senior reactor physicist, Anatoly Dyatlov, the deputy chief engineer overseeing the test, ordered the operators to raise the power as quickly as possible. The operators withdrew the control rods almost completely from the reactor core, far beyond what the safety regulations permitted. The minimum number of control rods that should remain inserted in the reactor at all times was 15. By 01 hours, only 6 to 8 rods remained in the core. This was a severe violation of operating procedures, but the operators were under enormous pressure to complete the test, and Dyatlov insisted on proceeding. At 01:23:04, the test began. The turbine steam supply was cut off to simulate a power loss. The turbines began to spin down. The cooling water pumps driven by the spinning turbines began to slow, reducing coolant flow through the reactor core. The reduced coolant flow caused the water to heat up more, and more steam voids began to form in the cooling channels. The positive void coefficient began to drive reactor power upward. At 01:23:40, the operators recognized that something was seriously wrong. The reactor power was increasing rapidly and was completely out of control. The senior operator pressed the AZ-5 button, the emergency scram button that was supposed to insert all control rods simultaneously and shut down the reactor immediately. What happened next was a consequence of another fatal design flaw in the RBMK control rods. The tips of the control rods were made of graphite rather than neutron-absorbing material. When the rods began to descend into the reactor, the graphite tips entered the lower portion of the core first. Graphite is a moderator. It speeds up the fission reaction rather than slowing it. For the first few seconds after the scram button was pressed, inserting the control rods actually increased the power in the lower portion of the reactor rather than decreasing it. This was the positive scram effect, and it was the final trigger. The reactor power surged to an estimated 3,000 megawatts, 10 times its maximum design power, in a fraction of a second. The extreme power surge caused the fuel to fragment explosively. The steam pressure in the cooling channels increased to catastrophic levels. At 01:23:47, a massive steam explosion destroyed the reactor and blew the 1,000-ton reactor lid, the upper biological shield, completely off the building. A second explosion followed seconds later, possibly a prompt criticality explosion as the fuel itself underwent a supercritical nuclear excursion. The reactor was destroyed, the graphite moderator was ejected and caught fire. Burning chunks of reactor graphite and fuel landed on the roof of the adjacent reactor building and on the surrounding grounds, starting fires across the site. The first responders were firefighters who arrived within minutes, not knowing that they were fighting a nuclear fire. They had no protective equipment adequate for the radiation levels they were encountering. Many received lethal doses of radiation within hours. 2 plant workers died immediately from the explosions. 28 more died in the following weeks from acute radiation syndrome. The firefighters and emergency workers who contained the initial fires are considered heroes in Ukraine and Russia to this day. The Soviet authorities initially attempted to downplay the severity of the accident. The evacuation of the nearby city of Pripyat, home to 49,000 people, including most of the plant workers and their families, was delayed for 36 hours after the explosion. When the evacuation finally came, residents were told to bring only what they needed for 3 days. Most never returned. Pripyat remains an abandoned ghost city today, a haunting monument to the disaster preserved almost exactly as it was on the morning of April 27, 1986. The immediate response to the disaster involved tens of thousands of workers called liquidators. Helicopters dropped sand boron and lead onto the burning reactor to smother the graphite fire and reduce radiation emissions. Miners tunneled under the reactor to prevent the molten core material from reaching the groundwater. Robots sent to clear radioactive debris from the roof malfunctioned due to the intense radiation. Human workers, given the grim nickname biorobots, were sent onto the roof in shifts of 90 seconds each to shovel debris by hand. The liquidators received radiation doses that caused long-term health consequences for many of them. A massive concrete and steel sarcophagus was constructed over the destroyed reactor within months to contain the radiation. This structure was built under extreme conditions by workers receiving significant radiation doses. The original sarcophagus was never intended to be permanent. It was an emergency measure. In 2016, a new containment structure called the New Safe Confinement, a massive arched steel structure 108 meters tall and 257 meters wide, was slid over the old sarcophagus. This structure is designed to last 100 years and to allow the eventual removal of the radioactive material inside. The Chernobyl disaster had consequences that reached far beyond the immediate death toll and environmental contamination. It exposed the fundamental dishonesty of the Soviet system, the concealment of the RBMK's design flaws, the suppression of safety concerns, and the culture of secrecy that prevented operators from understanding the dangers of their own reactor. The disaster severely damaged public confidence in Soviet institutions and is widely regarded as one of the events that contributed to the eventual collapse of the Soviet Union. The global nuclear power industry was transformed. Safety standards were completely reviewed worldwide. The RBMK design flaw was finally acknowledged, and all remaining RBMK reactors were modified to eliminate the positive void coefficient at low power. The concept of defense in depth, multiple independent safety barriers, each capable of preventing catastrophe on its own, was strengthened and codified in international nuclear safety standards. Operator training was fundamentally reformed to ensure that crews understood not just how to operate their reactors, but why the safety rules existed and what would happen if they were violated. The exclusion zone around Chernobyl has become one of the most unusual places on Earth. Without human activity for nearly 4 decades, nature has reclaimed the area. Forests have grown over abandoned villages. Wildlife has returned in remarkable numbers. Wolves, lynx, and even bears have been observed within the zone. The city of Pripyat stands frozen in time, its apartment blocks, schools, and amusement park slowly being consumed by vegetation. Paradoxically, the exclusion zone has become one of the most biodiverse areas in Europe despite its radioactive contamination, demonstrating that even the worst radioactive contamination is less damaging to wildlife than the continuous pressure of human habitation. The Chernobyl disaster teaches us that nuclear power is not inherently dangerous, but that nuclear power operated under conditions of secrecy, institutional dishonesty, and inadequate safety culture absolutely is. The RBMK's design flaw was known. The danger of low-power operation was documented. The positive scram effect had been calculated. None of this information reached the operators who needed it most. They made decisions that night not out of ignorance or carelessness, but because the system they worked within had failed them completely. That is the legacy of Chernobyl. We are Mech Cosmos, Engineering, explained. Subscribe now before we show you what the reactor looked like in its final seconds. Because every machine has a story, and sometimes that story changes the world.